Alright, last video in this chapter. We're talking about accumulation functions, and accumulation functions are functions that have a definite integral inside of it. Okay, you're not used to seeing functions with a definite integral in it. So typically you see something of this form, where in the bottom here, our lower bound is going to be a constant, our upper bound is going to be a variable, and then we have a function with a different variable on the inside. So notice how this particular one is in terms of t. So there's a couple different ways we're going to use these accumulation functions. The first one deals with constructing a function with a given derivative and value using our knowledge of the fundamental theorem of calculus. So here is our example. We want to find a function in the form of y equals f of x, given that its derivative is the tangent of x, and we know that f of 3 equals 5. So that means the point 3 comma 5 is on the function. Well, we're going to use an accumulation function here to help us. So here's what it would look like. Alright, so f of x is equal to, if we were to create an accumulation function with, now notice how the x value here is 3. If we put that 3 or that constant down the bottom, and we just slap an x up there for our upper bound, okay? And then if we were to put our derivative on the inside, but let's use a t or some other variable, just don't use an x, okay? If we just think about this for a moment, okay? If we were to plug 3 into this, f of 3, well, if I drop the 3 in for my upper bound where I see an x, I would have the definite integral from 3 to 3, which we know would be 0. Well, I'm told that f of 3 is 5, so I need to bump this up by 5. Alright, so that f of 3 is equal to 5. So that means I would have to add a 5 onto that accumulation function. So this is my answer. Let me just circle this. Okay, this would be my function that has a derivative of tangent of x. Now let's just check this. If this is our derivative, remember, if I were to find f prime of x, which is the derivative of f of x, well, if I'm taking the derivative of this integral, we know that that integral and this dt, they're going to wipe each other out, and we know that this x is going to get dropped in right there for the t. We would be left with the tangent of x, so that checks out. Okay? And by the way, the derivative of 5 would be 0, so that's why that has disappeared. Alright guys, take a moment to hit pause and copy this all down. So we're talking about a function here, h of x, and it's another accumulation function because we have a definite integral in it. And notice on the inside of this accumulation function we see f of t, and f of t is graphed for us. And we're told that we have some quarter circles here from 0 to 1 and then from 1 to 2. And we're first looking to find h of 2. Well, remember this is a graph of h of x. So if we're looking to find h of 2, that means we're going to simply plug in a 2 where we see an x. So that means I'm going to have the integral from 1 to 2, and then f of t dt. So what that means is to find the area from 1 to 2. Well, if we look at our graph here, from 1 to 2, that's this region down below, okay, that we said here is a quarter of a circle. So the area of a circle we know is pi r squared. And if it's a quarter, we're going to take pi r squared and divide it by 4. So in this case here in our graph, our radius would be 1, because we can see here that it goes down to -1. Alright, so the radius there is 1. So that means we're going to have a simplified answer of pi over 4. But be careful, this is going to have to be negative, because this region is below the x-axis. So we're not asked to find the area, we're asked to find the value of h of 2, which is a definite integral. So a definite integral can be negative. Now, next up is h of 0. So again, this is the equation for h of x. So h of 0 would involve putting a 0 in where we see an x. And the only place we see an x is that upper bound. Well, notice that the bounds are not in the correct order. We should always have the smaller one on the bottom, the bigger one on the top. So we can easily switch that and make that happen by negating that definite integral. Recall we said that was a property. So we're talking about finding the area from 0 to 1, which is this region up above. Okay, and again, it's the same as what we just talked about. It's another quarter of a circle, so it's pi r squared divided by 4. We already found that region to be pi over 4, so it's really the negation of pi over 4. This region is above, so it's positive, but there has to be a negative in front because we had to reverse our bounds. Okay, so that is negative pi over 4. All right, next we have h prime of 2. Well, if I am going to find the derivative here, h prime of x, okay, this is what we were talking about before. If I take the derivative of each side of this h of x equation, the derivative of h is h prime of x, and then the derivative of this definite integral here, well, the derivative would cancel out with the integral, and we talked about how that upper bound of x would just fall into the function where we see an x, and of course the dt would be gone. So really f of t becomes, it's an equal sign, becomes f of x, and this is really the same as h prime of x. So what we typically see in these questions is a whole bunch of stuff, a whole bunch of parts where they ask us about h. They might ask you things like, where does h have a min, a max, an inflection point? Where is it concave up, down, increasing, decreasing? You simply need to know that this graph that they give us, which originally we were told is just f of t, that's the same as the derivative of h. If there's one thing to take away from this, if there's only one thing that you're capable of remembering, remember that this given graph, right, the inside of this definite integral, which is always going to be f of t, that is the same as the derivative of your function. So if we're asked to find h prime of 2, h prime of 2, well, 2 is right here. That is simply the y value on our graph. So this would equal negative 1. All right, let's just write ourselves a little note. This is the y value on the graph. Okay, and remember the graph is h prime of x. Okay, finally here in this first part, h double prime of 2. We want the second derivative. Well, that's the derivative of the derivative. Remember, this is the first derivative graph. So the second derivative is really just the slope of the tangent line. Well, that is going to be 0 in this situation because it happens at a relative min. All right, so this is really the slope value at that point. And by slope, I'm really referring to slope of the tangent line or the derivative. Okay, next we're going to make a sign diagram for h prime, and then we're going to use it to analyze h. So take a moment and do that, and let me just get you started here. Okay, this is bound between 0 and 8 for those x values. Okay, so we don't have any information beyond it. All right, so if you want, you can shade, indicating we don't care about that region. Go ahead and make a sign diagram. So hopefully you agree with this sign diagram. At x values of 1 and 3, the derivative is 0. Remember, this is a graph of h prime. So between 0 and 1, the graph is above, so that's why it's positive. Between 1 and 3, it's below, so it's negative. And then between 3 and 8, h prime is above, so it's going to be positive. So what that really means is that right here at 1, we're going to have a relative max. At 3, we're going to have a relative min, okay? And we can also see where h is increasing. Okay, it's increasing from 0 to 1, and then from 3 to 8. And we can see that h is decreasing from 1 to 3. Okay? Again, the min and the max points, those are points on H. All right, take a moment and now do the same for H double prime. Okay, so hopefully you agree with me. So we are looking at inflection points at 2 and 6, because at 2 and 6 we really have a min and a max on our graph. Remember, the graph is H prime, so the derivative of that would be H double prime. So 2 and 6 we have an H double prime, or a second derivative value of 0. And then we can see the signs are going from negative to negative, because your tangent line slopes are going, or the function itself is going down, then it's going up, and then it's going down. So your slopes are either negative or positive. Okay, so that means we're concave up between 2 and 6, concave down between 0 and 2, and 6 and 8. Okay, so you have to be able to analyze this graph. Remember, you're going to be given this equation. All right, in this case it's h of x. The graph that you're going to be given is going to be of this inside piece. You need to know that this graph is the same as the derivative of the main function on the outside. Okay, bye-bye.